In this video tutorial, we will introduce the topic of stoichiometry. Stoichiometry is the study of mass-mole number relationships in chemical reactions and formulas. Let's take a look at this example here. This is my recipe for making a burger. You need a bun, you need a cow, and you'll make a burger. But you'll notice there's something missing from this recipe. It's not balanced. I actually need 2 buns for every 1 cow in order to make 1 burger. We refer to these values, these coefficients here, as a stoichiometric ratio. It's not good enough to just tell me what the ingredients are, you have to tell me the quantities involved of each. Now, once you have this initial ratio, you can start to scale things up. So if I have 4 buns, how many cows would I need and how many burgers would that make? Since the initial ratio was 2 to 1 to 1, the new ratio would be 4 to 2 to 2. But these are nice pretty numbers. Let's try something a little uglier. If I want to make 5 dozen burgers, how many dozen cows and dozen buns would I require? Again, we look back at our original ratio, 2 to 1 to 1. There's going to be a 1 to 1 ratio between burgers and cows, so that means 5 dozen burgers requires 5 dozen cows. Meanwhile, it's a 1 to 2 ratio between burgers and buns, so you'd have twice as many buns, 10 dozen. Now let's make the numbers really ugly. If I have 3.2 times 10 to the power 23 cows, how many burgers would I make? Because it's a 1 to 1 ratio, these two must be identical. Whereas over here, it's a 1 to 2 ratio between cows and buns, so you're going to have twice as many buns, 6.4 times 10 to the power 23. Same thing over here with moles. If I have 6 mole of buns, how many mole of cows and burgers would I have? Again, it's a 2 to 1 to 1 ratio, half as many each time, so you'd have 3 moles here and 3 moles here. This essentially is stoichiometry. So long as you have the initial stoichiometric ratios, which we can obtain by balancing the equation, so long as I give you that initial ratio and I give you another number, you can make predictions on what the remaining values are. So what the new ratio is. Now, when you set up your new ratio, it's important that you keep things consistent. If you put buns in the numerator on this side, you must keep buns on the numerator on that side. Cows in the denominator, cows must be in the denominator. Don't switch things up where you put buns on the numerator, but then on the denominator for the next one. You will not set up a proper ratio that way. Another recommendation I have is to keep your unknown in the numerator. So what are you trying to calculate for? Or in this case, the number that you want. And then keep your known values, the numbers that you have, in the denominator. This just makes your calculations easier, especially if your algebra skills are not that great. Now let's take a look at this new situation. If I have 4 grams of buns, how many grams of cows do I need and how many grams of burgers do I create? Well, if you use the original stoichiometric ratios, you would get a 2 to 1 to 1 ratio, so this one must also be 2 to 1 to 1, where it's going to be half as many cows and half as many burgers. But there's a problem. This doesn't make sense. How can you have 4 grams of buns with 2 grams of cows, but only make 2 grams worth of burgers? Shouldn't it be 6 grams? How is it possible for you to have a bun and a cow, but then your burger's lighter than the ingredients themselves? It doesn't make sense. And that's why mass ratios don't work. You can't take a direct route to calculating this. No. This only works for counted values, not for mass values. Because the direct path doesn't work, we need to take a little bit of a detour. As I mentioned before, if you have no clue what to do, convert to moles. Once you have converted to moles, mole ratios work. That's fine. You can do your ratios across to find the number of moles of burgers. Then from there, you got to re-pop it back out, converting moles back into mass. All right? So remember, mass ratios do not work. They don't make sense. You must convert to a mole. Then you can do the mole ratios. That makes sense. But then from moles, convert back to a mass. So let's apply what we just learned to atoms now. First step, balance your equations. There is no chemical equation from this point on that doesn't require balancing. If you do not balance your equations, you're going to have a bad time, because everything will just be a 1 to 1 to 1 ratio. And then suddenly you go, oh sir, the test was so easy. Oh, that's when I start to cry knowing that I'm going to have to mark your test. So please remember, we balance the chemical equations in order to get the proper stoichiometric ratios. Because without the proper stoichiometric ratios, everything else is incorrect from that point on. Alright, so the original stoichiometric ratio is a 2 to 1 to 2. So if I have a new ratio of 8 over here, then this one must be half as much, which is a 4. And this one is going to be a 2 to 2 ratio, so they're identical. So then this one must also be identical as an 8. Over here, if I have 3 dozen over here and it's twice as much to go to the other side, this should also be twice as much. While this one over here is going to be half as much, while from here to here, they are identical. 2 to 2 ratio, 3.5 10 to the power 22, 3.5 times 10 to the power 22. Now, as we saw earlier, I can't just do the 4 grams, 2 grams, and 4 grams over here because the mass ratios do not match up. They don't work. So we have to take a detour into the land of the mole, tunnel through to the other side, then pop back out, converting moles back into mass. So let's do this. First step, convert the mass into a mole. So mole is equal to mass divided by the molar mass. We've got the mass, 4 grams. Molar mass is 2 times 1.01 because hydrogen is diatomic, and notice how it is by itself, so you're allowed to have it as diatomic, H2. And there's 2 hydrogens, so 2 times the 1.01 grams per mole. Again, we can find the 1.01 grams per mole from our periodic table. Divide those two numbers and you get 1.98 moles of hydrogen. Now, since I know the ratio of hydrogen to oxygen is a 2 to 1 ratio, there will be half as much oxygen as there is hydrogen, making it 0.99 moles of oxygen. From there, we rearrange the equation so that mass is equal to mole times the molar mass. The mole value is 0.99 moles of oxygen. Molar mass, because oxygen is diatomic, so 2 times 16 grams per mole. The 16 grams per mole we can find from the periodic table. And the answer becomes 31.68 grams. And that, of course, is a much different answer than if we had just done our ratios 4 to 2 to 4. Now, obviously, I didn't factor in sig figs over here. I kind of goofed up and only had 1 sig fig on this value. But on a test, you would have a minimum of 3 sig figs. So you know what? Let's change this to 4.000 grams. And now we have the proper number of sig figs. But anyway, let's recap. We cannot go directly from here to there using our ratios because mass ratios do not match up. They don't work. Each substance has a different molar mass, so we can't treat them all as equals. To get around this, we need to take a slight detour into the land of the mole. Mole is equal to mass divided by molar mass. Molar mass we can find from the periodic table. Don't forget that they are diatomic elements sometimes. Once we have the mole value for this, we can convert it using ratios into the mole value for this. Once you have the mole value for what you're trying to find, convert it back into a mass using the equation mass equals to mole times molar mass, and you're good to go. All right, so that covers simple stoichiometry. What I would like you to do is try out these sample questions over here. You will require knowledge of nomenclature and predicting chemical reactions because they don't actually give you the chemical reaction itself. And of course, don't forget to balance those equations once you've written them in order to obtain the original stoichiometric ratios. Now, if you look at the back of the sheet, you'll find answers. So please check your answers before you do the whole sheet wrong. Confirm that A, you have written out the chemical formula properly and predicted it properly, and also balanced it properly before you even start doing the stoichiometry. Now, of course, there's the answers on the right-hand side. In our next video, we will discuss stoichiometry with limiting reagents as well as percentage yield.